Okay, so we're back for the continuation of problem 1.24. And so here we are in the middle of still step A, where we want to calculate the total number of argon atoms in the Earth's atmosphere. And so in the interim, I went ahead and just rearranged the ideal gas law to get the number of argon atoms that came from Caesar's last breath. So that's probably the most straightforward part of this whole problem, and if it's not obvious for how to do it, I encourage you to sit and think about it. I'm sure you're all capable of doing it. So what I came up with is that in Caesar's last breath, he exhaled 1.8 times 10 to the minus 4 moles of argon, and we might actually want that expressed in terms of argon atoms later, so that is also the same as 1.09 times 10 to the 20 argon atoms. So quite a few argon atoms came out of Caesar in his last breath. Okay, so now let's see if we can figure out how many argon atoms are in the universe. Not the universe, sorry, the Earth's atmosphere. And so remember what we're going to do is we are going to integrate this expression over the coordinate that takes us from the surface of the Earth to the edge of the Earth's atmosphere. And so we're going to express P of argon as a function of distance in this particular way. And I've already kind of broken up the expression, so let me just write this down really quickly. So this comes from an earlier problem where they say that the pressure of some gas, so I'm just going to write some gas G, is equal to the pressure of that gas at the surface of the Earth times this exponential of negative molar mass of the gas times the acceleration due to gravity times z, the distance from the surface of the Earth, all divided by RT. Okay, and this would also be another expression whose dimensions you should absolutely check. Okay, I'm not going to do it here. Let me just take like 30 seconds to walk you through it though. Big M sub G, this is molar mass, so this is going to be in mass over moles. G, that's the acceleration due to gravity, so that's going to be like length over time squared. Z, that's just distance, and that's length. R, we did last time. T, we did last time. Okay. T is just T. R is very complicated. I'm not going to recite it from memory. The key thing is that whenever you take an exponential, the argument to the exponential should be overall dimensionless. So what you're looking for is that all the dimensions cancel when you multiply the dimensions of m by g by z and divide by r and t. And then, of course, over here, we've got a pressure. So we know we also went through the dimensions of pressure before. Pressure times the dimensionless thing is just the pressure. Okay, so that's what you should see. Okay, so check that on your own. Now, a couple of other things. Do we know, when we want to do this for argon, do we know this P argon naught, right? The pressure at the surface of the Earth. Well, yeah, we basically do. So we know that from the details of Caesar's last breath. He was at the surface of the Earth. The total pressure at the surface of the Earth is 1 atm. So what's the pressure of argon at the surface of the Earth? It's going to turn out to be the mole fraction of argon multiplied by the total pressure at the surface of the Earth. Okay, so they tell us the mole fraction of argon, which is basically 1%. And so n argon over n total, and what goes into n total? Well, everything else in the atmosphere. So N of CO2, N of oxygen, N of nitrogen, N of water, N of argon, etc. So N total is just the summation of all of those things. And so N argon over N total is 0.01. And so then P argon is 0.01 times pressure that Caesar experienced, which is 1 atm. So pressure of argon is 0.01 atms. I went ahead and converted that into pascals because that's going to help us out a little bit later. So in pascals, that's 101 That's 1,013.25 pascals. Pascal also is a kilogram per meter per second squared. Okay, so that's what our P naught is. Okay, A we already calculated. That's the surface area of the Earth. R and T we already know. So then what we're going to need to do is actually integrate this expression. Okay, and so you may have this integral memorized, maybe not. It's actually a pretty simple integral, but I don't care if you have it memorized. You can stick it into Wolfram alpha. But what it works out to be, I'm going to write our constants again. PAR 0 A over RT. Okay, times the integral, which will work out to be negative RT over M of Argon times G times exponential of negative M AR times G times Z over RT. And then this is a definite integral. I need to evaluate it at Z equals infinity. Oops. I hope you can see that, and Z equals 0. Okay. What I can realize immediately, if I think about the limits, okay, of this exponential, right? When Z is equal to infinity, then I have exponential of negative infinity, which is 0. When I have Z is equal to 0, I have exponential of negative 0, which is equal to 1. Okay, so the upper limit actually goes to 0. The lower limit goes to 1. So what I end up getting, and of course I take this thing evaluated the upper limit minus this thing evaluated the lower limit. So I've got basically this whole thing evaluated the limits is 0 minus 1. Okay. So then what that means is that overall, when I work out all of my terms, I'm going to have a negative hitting this negative sign. So this is going to turn it into a positive. Okay. So P of Argon 0 A over RT times RT over M of Argon times G. Okay? And we can see that our RTs cancel. And what we're left with then is just P of Argon at the surface of the Earth times the surface area of the Earth over R. Sorry, not over RT, because my RTs cancel. Over mass of Argon times G. Okay? So we're going to evaluate this. Of course, I'm going to need some more space to do this. So let me go ahead and make that space by erasing this stuff. Okay, so what's P of Argon at the surface of the Earth? That's going to be 1,013.25 kilograms per meter squared per meter per second squared. So let's just write this thing up here. PAR 0 times A over MAR times G. Okay, and what is this whole thing equal to? 1013.25 kilogram times meter to the minus 1 times second to the minus 2, right, times this number, 5.08. I'm already running out of space. This is too tiny.
Are you busy?
Yes.
Okay. When's a good time for me to come back? Because we're working in the lab in 4001. Thank you so much.
Can you bring it back?
Yeah, thank you.
Okay, so let's rearrange this. Okay, so down below, this is 1013.25 kilogram times meter times second to the minus 2, okay, times 5.08 times 10 14 meters squared over. What's the molar mass of argon? So it's approximately 39 point, let me check my numbers, 95 kilograms. And then finally, what's G? 9.8 meter second squared. Right? Meters per second squared. Okay, so let's check our dimensions. Let's check our units real quick. So at the end of the day, we should be hoping to see something which looks like moles. Oh yes, here we go. So this is a molar mass. So kilograms, mole, minus 1. There we go. Okay, so I've got kilograms, cancel kilograms, right? I've got meter squared here, meter minus 1 here, and meter in the denominator. So these all cancel each other. And then I've got second to the minus 2 and second to the minus 2. Okay, so this works out to be a number which, to the best of my calculating ability, is in argon total is equal to 3.28 times 10 to the 14 moles. Okay. So that's the total amount of argon in the atmosphere. Okay. And then this is the total amount of argon in Caesar's last breath. Okay. So now we're in a position to go ahead and work out B, which is the fraction of argon from Caesar's last breath in the universe. Okay, so let me put a little box around here. So what's our fraction? Right, fraction of argon from Caesar's last breath to argon in the entire atmosphere is going to be basically equal to it's going to be moles of argon from Caesar, which is 1.8 times 10 to the minus 4 moles. Divided by total number of moles in the universe, 3.28 times 10 to the 14 moles. Okay. And so we can crunch that number, which I should do. 1.8 minus 4 divided by 3.28 14. Okay. So I find this fraction to be 5.4 times 10 to the minus 19. Okay. Now, what we can do is take this fraction and multiply it by the number of argon atoms in a typical breath, and that will be basically the number of argon atoms in a typical breath which came from Caesar's last breath. So why am I using the same number? Well, I'm going to assume, and I think it's a relatively good assumption, that the same number of atoms of argon that Caesar breathed in a 450 centimeter cube breath will be the same number of argon atoms that we breathe in the same volume breath. And the reason being is that the pressure of the atmosphere has not changed. The temperature of the atmosphere has not changed from his last breath until now. And we're assuming it's 300 Kelvin and 1 atmosphere. And then furthermore, the actual composition, the mole fraction of argon has not actually changed. It's still 1%. Okay? So then basically what I'll write is num in from Caesar's last breath is going to be equal to fraction times in argon and a breath. right? And so that's going to be this number, 5.4 times 10 to the minus 19 times 1.09 times 10 to the 20, okay? So go ahead and crunch that number while I do the same. Okay, and what I get is 58.6. Okay, so what does this mean? That means every breath, at least under the fraction that we calculated, every breath we take, 58.6 argon atoms actually come from Caesar's last breath. Okay, so that's quite a few. Okay, and now the only thing that we need to do then is take the reciprocal of this number to figure out how many breaths we have to take to get exactly 1. And so since we know that for every single breath we get 58 argon atoms from Caesar, then in fact we're going to have to take far fewer than a single breath to get an argon atom from Caesar. So 1 over 58.6, right, is going to be 0.17. 0.017 breaths. Okay, so this is the number of breaths required to get approximately 1 argon atom that came from Caesar's last breath. So it's a pretty remarkable result. So evidently we are constantly breathing argon atoms that came from Caesar's lungs. Okay, I hope this was helpful. I'm going to post these, and I encourage you to watch them. I guess if you're listening to me say this, that means you've watched them. Okay, thanks a lot. Talk to you later.